Alright, so now we are about to do the third part of the semiconductor devices, which is transistors. Now transistors, we have lot many applications, like it can be used as a switch, it can be used as an amplifier, it can be used as an oscillator. As we advance from switch to oscillator, the construction will get a little bit more complicated. Alright, so I want you to do this class with utmost attention and please keep taking notes as and when required. Okay, those who have already, those whose this part is completed, please refer to your notes and keep learning. Okay. Okay, fine. So let's talk about the transistor. Transistor meaning, transistor is actually a device. It is a combination of three different semiconductors, right? It has got three terminals and two junctions. So let's write down transistors. Okay, this topic is very very important for NEET. If you look at the previous year questions, not many questions have been answered from this one. Alright. So the first topic, the first point that I'd like to add to this is it is a three-terminal and two-junction device. Two-junction device. It is of two types, NPN and PNP. So you can see three different semiconductors are there, right? Two N semiconductors, N-type semiconductors sandwiched with a sandwich of P type. N-type sandwich between two P types. Alright, so this is the you can say um, two types of these are the two types of semiconductors transistors which are available. So first point is three terminal and two junction device. Okay, let's look at the symbol. It's very simple. No need to make it too complicated. You can see three terminals are there. Alright, three terminals are there. The one which is sandwiched between the two, the one which is sandwiched between the two is basically your base. Okay, the one which is let me just correct the diagram. There is a slight error in the diagram. You know that the collector region has to be the broadest, right? The emitter region is, yeah, so now it's alright. So the doping in all these three regions is different, as well as the area, as you can see, that is also different. Area is also different. This largest area will be your collector terminal, and the medium area will be your emitter terminal, and the thinnest one will be your base. Alright, thinnest one will be your base. Now this is the correct, you can say, representation. So let it be NPN. For PNP, PNP, again this is the base, this is the emitter, and this is the collector. Right? So it does, this much is easy for you to understand. So let's talk about the doping of the base, emitter, and last but not the least, the collector. Right? I'm writing doping levels. You can make it like a column for easier understanding and memory. Base is the thinnest region, yes or no? It is the thinnest region, right? And of the device, it is the thinnest region of the device, and it has low doping. What kind of doping? It has low doping. Emitter, if you talk about the emitter, it is heavily doped. Heavily doped. And if we talk about the collector, it is moderately doped and very large in size. Moderately doped and of course large in size. Large in size. Alright, if you've understood this much, let's move on to the next. Let's move on to the next slide. Just a second. Let's talk about the circuit symbols. We have understood more or less what our transistor will look like, right? There are three regions. What are the doping levels of each of the region? What is the size of each of the region? Yes or no? What each of the region is called? Yes or no? There are two junctions. We looked at the two junctions. We looked at the three terminals. Two junctions meaning one junction is between the emitter and the base, and the other junction is between the base and the collector. Simple enough. Alright. Now let's talk about the circuit symbols then. The circuit symbols, people generally get confused with this, but just remember one particular sentence so that you can make the circuit symbol properly. Okay, the sentence is that current always flows from P to N. Current always flows from P to N. This you have to remember while constructing your circuit symbol. So circuit symbol will, let me write down the common skeleton of the circuit symbol. Okay, this is the skeleton of the circuit symbol. Alright, now you see a bridge like thing out here. This is your base terminal. Okay, okay. Now suppose you have, let's consider NPN, and out here we will draw the PNP. Okay, so let's write down the common skeleton first. Let's write down the common skeleton first, like this. Let me write BCE. Let me write that. Right. Okay, this is the common skeleton. Now the difference in between the arrow head will give you the difference between PNP and NPN transistor symbol, circuit symbol. The difference is that in NPN transistor, you know that this is the arrangement of the semiconductor regions NPN. So current always flows from P to N, right? So this will be the direction of the arrowhead. Alright. Now let's talk about for PNP. So PNP, this is going to be your regions, respective regions. You know that the current flows from P to N, so this will be your direction of the arrowhead. Alright. So this is the difference between your NPN and PNP circuit symbols. Alright. So arrow is kept in the direction of the current flow. Arrow is kept in the arrowhead is kept in the direction of current flow. Alright? Okay. Okay. Now let's talk about working of a transistor. Working of a transistor. Working of a transistor. Right? So when we are using transistor as a switch, first we are going to talk about switch. Okay, how transistor can be used as a switch. Okay. So when we are using transistor as a switch, then the BE junction that you have and the BC junction that you have, these are the two junctions possible for a transistor, right? The BE junction is kept forward biased and the BC junction is kept reverse biased. Alright, so you can like memorize this EFCR. So you can write it like the emitter is forward biased and the collector is reverse biased always. Okay, this is important to note before studying the working of a transistor. I'll be taking the entire circuit diagram and will be explaining to you in just a moment. Before that, to those who had been given this question in their test, why is collector kept large in size? Some of you could write the right answers, others gave very messy answers. Now, this particular question as to why the collector is kept large in size, okay, I'll just write it down for you. Why is collector kept large in size? Please note down the question in your margin or somewhere where it is easily noticeable. Right. Whenever high amount of charge carriers are collected in the collector, or you can write down when large amount of charge carriers, when large amount of charge carriers are collected in the collector, right? Collector region, heat dissipation will take place. Heat dissipation takes place, which can overheat the semiconductor and burn it, making it non-functional. Functional. That is why exactly your collector region is kept large so that you can have a greater surface area. Alright, therefore collector region where most of the majority charge carriers actually gathered, that collector region has to be made large. And of course it has to be moderately doped. It will be moderately doped. It cannot have very high doping because if it will have high doping then the concentration of the charge carriers will be increased. That is why it has moderate doping. Alright? Okay. Collector region has to be made large so as to increase the surface area. Surface area. Okay, surface area. So that it can accommodate large number of charge carriers without and it can also diffuse the heat dissipation which is coming. Alright. The surface area if it is large then the heat can transfer into a very large area as compared to a very crumpled space. Right? So that is about it. Alright, so we were talking about the working of a transistor. Let's just talk about the working of a transistor after looking at the circuit diagram. Okay, because without that it is very difficult to explain. So let's make the circuit diagram. Okay, so what kind of transistor should we use? Let's use PNP. Alright, you can use NPN also. The construction will follow the same principles. Everything will be the same only. Just you have to remember that the base emitter junction has to be forward biased and the base collector junction has to be reverse biased. Okay, this biasing is necessary to ensure the correct direction of flow of current. What? Correct direction of flow of current. So that ultimately our output is achieved at the collector terminal. Alright? Okay. Alright. Please have a look at this screen. You have PNP, right? In this particular case, PNP, we will take out another terminal from here. So 3 terminals have been created, right? And 2 junctions are also ensured. Now this is the base, this is the emitter, this is the collector. That's very clear to you, right? Now the thing is, we have to do forward biasing of the emitter base junction or base emitter junction. So this P will be connected to a positive terminal out here, right? So I completed making my input circuit. This is known as the input circuit, and my output circuit, which will involve the base collector junction, this has to be reverse biased. This is forward biased, P to positive, N to negative. Now this particular thing has to be reverse biased. So I am connecting P to N. Okay. So this is my reverse biasing. This is the output circuit and output circuit. This is negative. This is positive. P2 minus N2 plus. This much is clear. This will be called as your cathode since it is at a higher potential. This will be known as the anode. Okay. Now let's talk about the naming of the batteries. This particular battery, this will be called as your B. What will it be called? BEE, and this will be called as your BCC. Alright. The potential difference between your base and the collector will be called as your BBC, and the potential difference between your base and the emitter will be called your BBE. Alright? Okay. Now let's try to understand the direction of current flow. Now you know that the direction of current flow is basically from the positive to the negative, yes or no? Right? So you can see out here you have P, out here you have N. Right? So the IB is essentially going to come out from here. It is going to be directed in this manner, and emitter current is going to be in this manner. Okay, and the collector current will be in this manner. Simple. Right? If you try to look at the circuit symbol for this, that is also quite easy to make. This is the emitter, this is the base, and this is the collector. Right? This will be the direction because P and P transistor we are taking. From P to N the current will flow. That is why the entering of the current is shown by IE and the leaving of the current is shown by IB and IC. Got it? Okay. Now, you might be wondering, what is the function of this base out here? What is the function of the base out here? Because the current the current, the output current is basically your IC. Okay, IB, the magnitude of IB is actually 0.05 times of IE. Okay, the magnitude of IB is basically 0.05 times of IE. Okay, which is basically your 2 to 5% of your IE. 2 to 5% of your IE. This is the maximum amount of IB that can follow. Maximum amount of IB that can follow. That can be conducting. Okay, that can actually come out of the base. Okay, so you are fairly getting this idea that IE and IC, they are very, very high, greater in magnitude as compared to the IB. Okay, so in this particular P semiconductor, the holes are the majority charge carriers, right? Here also, the holes are the majority charge carriers. But in your N, the majority charge carriers is your electrons, right? Now, because of the recombination of small number of electrons, which are your majority charge carriers out here, okay, you can write down due to recombination, small current IB flows. Due to recombination, small current IB flows. Small current IB flows. Okay. Now the thing is, my IB is so small, it is negligible. Then what is the need of this base? What is the function of this base then? If it is not contributing that much to the overall current, then what is its function then? Okay, basically this base, the function of this base, you can give the heading function of base. Have you written down the recombination part? Because of the recombination of the small number of electrons which are present in the N region, the IB flows. Okay? Okay. Alright. So function of base. What is the function of base? Base is providing a forward bias conductivity. What is it doing? Base is providing a forward biased conductivity. Alright, it is providing a forward biased conductivity for holes, in this case where it is PNP transistor, holes on majority carriers, please write down, to pass through the base and reach the collector. So basically the base acts like a bridge between the majority charge carriers of the other two regions, that is the emitter and the collector regions. Alright, so if this base is not there, then you cannot ensure the forward biasing of the emitter. And if the emitter is not forward biased, then IE will not flow. If IE doesn't flow, IC will also not flow. Okay, so it's very important to have the base so that the input circuit can be forward biased. Alright, without the base, the input circuit cannot be forward biased. Alright, that is the point. Okay, now, or for that matter, the collector also cannot be reverse biased without the base, right? So that is the function of the base. But of course, IC is your output current, but IE, this is the input circuit, right? This is the input circuit. So IE is like your input. Okay, so basically if the input is not there, then how will the output arise? That is why we are focusing on the FB forward biasing conductivity for holes or the majority charge carriers. Alright, so basically the base will act like a bridge between the emitter and the collector. Okay, if you have understood that, let's move on and reach the collector. Okay, so please write down, very small amount of holes will recombine with small number of electrons present in base. Why so? Because low doping right? Low doping. Base is very lightly doped. Okay, so very small amount of holes will recombine with the small number of electrons present because of the low doping, right? And this particular phenomena leads to the flow of small current IB, alright, which is 0.05 of IE or 2 to 5% of IE. Alright, now the thing is, the excess holes, the ones that did not recombine with the electrons in your N region, they are going to reach the collector, holes reach the collector region and contribute to output current. Contribute to output current. You can write it down, output current. Okay. If this particular thing is clear to you, let me just change the screen. 1, 2, 3. In the collector region, negative potential exists because it is reverse biased. So collector region, due to reverse biasing, has negative potential, right? Okay. As a result, IC is generated. Therefore, IC is generated or the collector current is generated. Okay, so base was giving the bridge for the holes to pass from the emitter region to the collector region. So you can have a formula out here that IE equals to IB plus IC. And this formula is very, very important for your needs. The needs students, please have a look and note it down. Alright. So IE is approximately equal to IC because IB is 0.05 of IE, which is very, very small. Okay. So can we imagine a situation when the base is disconnected? Let's look at the diagram out here. Suppose I put a switch out here. And I disconnect this entire circuit at the base position, at the position of the base. Then what will happen? I'm disconnecting it. I'm using a switch out here and I'm disconnecting it. Then if the base is disconnected, what will happen? The input circuit will no longer be forward biased. Yes or no? Right? So the holes will not have the necessary push, to come to the collector region, right? Okay. So as a result, IC will be 0. Yes or no? The holes out here which actually get to the collector region and then they conduct and then they start conducting the electricity, that thing will no longer happen because the holes out here are not getting the required push to reach the collector region because this base has been disconnected and no longer the forward biasing is existing. Alright, so IC becomes 0. Okay, so obviously let me write down what if base is disconnected. Base is disconnected. What if the base is disconnected? What happens then? Please write down. FB, forward biasing of base emitter junction, will no longer exist. No longer be possible. Right? Therefore, the holes, please write down, therefore the holes will no longer be emitted by the emitter. Holes will no longer be emitted to the collector by the emitter collector region because the reverse biasing of the base puts base in a negative potential. Out here there is a higher potential, right? And out here there is a higher potential, and out here there is a negative potential. Yes or no? So the base being at a negative potential will allow the base current to pass through it, right? So base current will also be 0. IE will also be 0 and IC will also be 0. Yes or no? This is what happens when you disconnect the base. Alright. So isn't this working like a 1, 0, 1 meaning the output current will be obtained, 0 meaning the output current is not obtained. It's working like a binary, right? It's working like a binary device. Okay, where 1 is the output and 0 means no output. Right? So if you disconnect the base, then you will get no output current. If you connect the base, you will get output current. So this is actually the transistor working as a switch. You follow? This is actually what I meant by transistor being used as a switch. Okay, so you can write that down. You can write that down. You can write that down. Alright. So please give the heading use of transistor as a switch. As a switch. Please write down. A switch is provided with biasing. Is provided with biasing. Alright. Biasing to what? Biasing, reverse biasing the base. Sorry. Forward biasing the base emitter. Forward biasing the base emitter junction. Right? Leads to negligible base current. Leads to negligible base current. But EC conductivity, E to C conductivity, that means emitter to collector conductivity is established on reverse biasing the base collector junction. Okay. So basically, therefore, base acts like a potential bias to switch on the switch. Okay. Okay. Now please write down. DC gains of a transistor. Please write down DC gains of a transistor. Alright. So basically you will have DC gains when the transistor is used as a switch. Alright, and when transistor is used as an amplifier, later on when we will be studying after switch the amplifier, okay, at that time we will be studying about the AC gains of a transistor. Alright, transistor can be in short it can be written as TR. Okay. So number 1, please write down base current amplification factor. Base current amplification factor. The numericals for the NEET people, they will come directly from these questions. So it's very absolutely important to memorize these values. To know what IC is, to know what IB is, and to know what the beta is. It is the DC gain, alright. Base current amplification factor beta. Okay. IC by IB. And you also know that IC is very, very greater as compared to the IE. Right. So its value sometimes it ranges from 150 to 200. Okay, its value ranges from 150 to 200 value. Very high value basically. Beta has very high value. Very high value. And it's a ratio of 2 currents, so it is dimensionless. Okay. I hope you already figured that out. Second is emitter current amplification factor. Emitter current, I'm just giving the commas out here so that you can understand. Emitter current amplification factor alpha equals to IC divided by IE. Okay. So this value, it almost comes out to be 1. Because IC is more or less equal to IE because IB is very, very small. Yes or no? Okay. Now, questions are asked by providing either of the values. Like either they'll give you IC, IB value, they'll ask you IE, how much is the IE. or they'll ask about calculate the base current amplification factor beta. They will not write the entire thing like base current amplification factor. They'll just write beta or alpha. So you need to know that what beta is. It is the base current amplification factor. What is its formula? IC by IB. How is its values range? It is a very high value, sometimes 150 to 200. It's a ratio. Okay, so it's dimensionless. Then emitter current is alpha. Alright, and this we are talking about DC gains. So all of these things you need to understand properly. Now, please see, IC equals to IB, sorry, IE equals to IB plus IC. Okay, IE equals to IB plus IC. From here, you can easily write IE, just a sec, sorry, not IE, IC divided by alpha. IE can be written as what? IE can be written as what? IC divided by alpha, right? What can IB be written as? IB can be written as IC by beta, right, plus IC, right? So we can come up with the formula. This formula is very important. Two formulas we can come up with. Alpha equals to beta plus 1. These sometimes questions are asked directly from these particular formulas. Alright, so these particular formulas can be derived from this. Okay, so in one formula, in the first formula, I have expressed alpha in terms of beta. And in the second formula, I have expressed beta in terms of alpha. So please memorize these two formulas because either direct questions will come relating to the formula, they will ask you the formula, or they will ask you the value of alpha if beta is given. Okay, or maybe they will give you IC and IB values. You need to calculate beta and then you have to calculate alpha. Okay, so if this is done with, let's move on to working of a transistor as an amplifier. Okay, before that, let's talk about some graphs. Just a second, please. Alright, so we are supposed to start with the graph, right? Graph of, you can say, using transistor as a switch. Alright, so let me just draw again the transistor being used as a switch, the diagram for that. Please have a look. This diagram is a little bit different from the previous one, but then it has the same logic going on. Alright, so we have the base, collector, emitter. Alright, for this time we are taking an NPN transistor. Alright, we are taking a what? We are taking an NPN transistor. So our base right here is P. So P2 positive. So again this particular thing has been, you can say, forward biased, and E is of course at N semiconductor, so it has been reverse biased. Alright, now please have a look. This particular battery that I have out here, let it be a variable battery. Let it be a variable battery. So this is the input voltage, you can say, right? So I'm across this particular terminal, I'm attaching a, you can say, a voltmeter, and I'm measuring it as VI. So at different times we can have different input voltages. Since this is a variable battery, that is why I'm attaching the voltmeter so that I can measure and apply the voltage accordingly. Alright, now let's talk about the output circuit. Output circuit has to be reverse biased. So this is N. So with N, we will connect the positive so that it becomes reverse biased. Again, we will be using a variable battery, and of course this is our output voltage. So I'm writing V0. This is again a voltmeter. Just write it this way. Write it this way, V0. All right. So this particular thing is your BCC, correct? This is also a variable one because it will depend upon VI input. Yes or no? Alright, so basically what will happen now? What is the direction of the flow of current? This, right? So this I will say, let me write it as RB since it is base biased, and let me write this RC because it is attached to the collector. Alright, so you can see in a way that RB is your input resistance and RC is your output circuit resistance. Alright, so let's talk about the direction of the current. This is the direction of current. This is the direction of current. right? So, and this is the direction of current, right? So IC, IB and IE, all the direction have been mentioned properly, right? Now, since we want to write down the graph, the transistor actually works in three different regions. Three different regions. Okay. Along your y-axis, I'm writing V0, that is the output voltage, and along your x-axis, I'm writing the input voltage. Please look at the graph very carefully. This is a very important graph, you can say. Okay. So I am drawing two dashed lines, which are used to demarcate the working of the transistor in three different regions. The first region is known as the cutoff region. What is it known as? It is known as a cutoff region. Alright. And the last region is known as the saturation region. Saturation region. Okay. So this particular, this is basically the transfer characteristics of a base bias transistor. Okay. With respect to the voltage. So V0 and Vi. V0 versus Vi. So output voltage versus input voltage, we are trying to take the graph. So cutoff region, saturation region, and the middle one is known as the active region. What is it known as? Active region. So we are studying switch, right? So the switch will function in the first two regions. This region it will function, and at this region it will function. In this particular region, the cutoff region, which is, it will be in this particular region, you can see that V0 part is high and Vi part is low. Yes or no? Vi part is low. So what is the characteristics of this particular cutoff region? V0 is high, Vi is low. So if input voltage is low, just try to understand it logically. If input voltage is low, out here it is input voltage. If input voltage is low, can the IB flow properly? No, it is not sufficiently forward bias. Your input circuit is not sufficiently forward bias so that the IB will not flow properly. Alright, you can also comment that IB is almost equals to 0. Alright, now if IB is equals to 0, then IC will also be equals to 0. IC will also be equals to 0. Why is it so? Because if the forward direction current does not flow, then the emitter current will also not flow. Alright, both are linked together. Okay, so since IB is 0, IB can be called as your input current, and IC is of course your output current. Alright, so basically you can comment that if IB is 0, then IC will also be equals to 0, right? And what is your V0 equals to? V0 will be very, very high in this case, alright, which is equals to VCC, right? So in this particular stage, can you guess if it will be working in the switched off state or switched on state? Of course, it is going to work in the switched off state. Switched off state. So in the saturation region, you already concluded that it will be working in the switched on state, right? So let's look at the characteristics of the switched on stage. So in here you can see the Vi or the input voltage is very, very high, and the V0 comes out to be very, very low. Yes or no? Okay, so since the Vi is high, that means the emitter base junction is sufficiently forward biased. Yes or no? It is sufficiently forward biased. Now if there is sufficient forward biasing in the saturation region, that is, then the collector current will flow. IC will flow and IB will also flow. Okay, input current will flow, as a result output current will also flow. Alright. So as a result, you can say that the output voltage V0, it almost decreases to 0. This almost tends to 0. Alright. The input voltage, it is becoming very, very high, and the output voltage is becoming very, very low. Alright. So from greater potential to lower potential, the current will start to flow. That is the rule. Yes or no? Please try to understand what I am saying carefully. If not, then please replay it. Okay. So basically what happens when the transistor is in the saturation state, okay, whenever it is in the saturated state, you can say maximum IC is flowing. IC is maximum and no more IC. Not even 1 milliampere amount of IC extra can flow now. Alright, so this is the maximum IC flowing through the transistor. So this is obviously in your switched on state. Okay. Okay, so basically Vi has to be high enough to drive the transistor into the saturation state. right? And at that point, the V naught is going to become low, that means nearly zero, right? In this particular state, your whenever it is in the saturation state, that means IC is maximum. In that particular state, you can say that the transistor is conducting and it is in the switched on state. However, in the cutoff region, when the VI is very low and VO is very high, right? In that case, IB equals to 0, so IC will also be equals to 0. So switch is off at that time. Alright, so basically this is the complete understanding, you can say, about the transistor working as a switch. Now obviously in computers and other electronic devices, you have very millions of you can say in a particular time frame, these transistors can be switched on and off around a millions of times in a particular time frame. Alright, so they are very more efficient. They are very much efficient, and of course they are small and they are cheap. They are long lived. Alright, so many types of advantages you get by using transistor as a switch than to using the you can say the conventional switches like the reed switches or the relays. Alright, so that's what I want to tell you about switches. I hope this part is clear to you, and switching action of a transistor is also clear to you. If it is not, then I'll just make you write a flow chart. Maybe that will make everything clear. That will give a gist of everything that is happening. Alright, so please write down, if Vi is high enough, if Vi is high enough, that means if Vi is high enough, then what happens? V naught is low, almost equals to 0. Right, almost equals to 0. Please copy down from here the flowchart. This will help you understand the switching action of a transistor. You can give the heading, switching action of a transistor. Switching action of transistor. Transistor. This graph is absolutely important. The graph out here is absolutely important because it will help you to understand in which region the transistor is used as a switch. That is in the cutoff region and saturation region. Out here it is off and out here it is on. So what is the active region's function actually? This in the active region, the transistor is used as another device which is called the amplifier. Alright, this is called the amplifier. So we'll be taking this amplifier next. Okay, we will be taking up the amplifier in the next study. For now, let's continue with the flowchart out here. So out here you can see Vi is there. Vi, if it is increasing, then V naught is very, very low, almost equals to 0, right? So in this particular case, the EB junction is sufficiently forward biased. Sufficiently what? Sufficiently forward biased. Alright, forward biased, so that IB flows and IC also flows. IB is the input current, IC is the output current. Input current. Okay, this is the output current. Right, this is the output current. IC also flows, and IC will be maximum. And this is known as the saturation region. This is known as the saturation region in which the transistor is working. Alright, so transistor is switched on. Switched on. So the reverse one, if you want to take, like Vi is very, very low and V naught is very high. Is very high. High. Alright. So in this particular case, your I is at a Vi is low and VO is high. So will the current flow? No, it will not flow. But in this particular condition, your Vi is high, VO is low. That is why the current flows. Alright, that is why the current flows. Okay. So Vi is lesser, V naught is very high. As a result, what will happen? EB junction not sufficiently forward biased, So IB, which is your input current, is 0 and IC is also 0 as a result. So we can say that the switch is working in the cutoff region now, and therefore it is switched off. Okay, switched off. The circuit will be switched off. Alright, so I hope this flow chart explains to you the working of a transistor. If this is done, let's take to the next topic, which is your working of a transistor as an amplifier. Now before explaining the working of a transistor as your amplifier, I would like to explain about your configurations different configurations in which transistor can work. Principally, there are three different configurations in which transistor can work. Alright, one is common base amplifier, common emitter, or you can say common base configuration, common emitter configuration, and common collector configuration. Alright, so these three are the different configurations in which your transistors can work. Alright, so on the basis of the different configurations, there are different types of amplifiers as well. Okay, so please write down the topic transistor connections as an amplifier. Transistor connections as an amplifier. Alright, so I will explain to you what an amplifier is, although you already know what an amplifier is. Amplifier is an electronic device that can amplify the amplitude of any signal. Okay, of any signal. So it is basically used for amplification of signal, input signal. Amplification of input signals. Now these signals can be audio signals. Mostly it's used for audio signals. Alright, like for example, the microphone that I am using right now, which I have no clue if it is functioning properly or not. The microphone that I'm using right now, it has got an amplifier. It is capturing the sound energy. It is converting it into electrical energy, amplifying the amplitude of the alternating current so obtained from the sound energy. Okay, that is the function of the amplifier. Now, once the amplitude of the sound signals which have been converted into the AC has been increased, it can be transported into another, you can say it is transported into obviously my laptop, which is actually recording it, and then when you're listening to the this particular video and the sound is being transported to your ears, the amplified signal is coming out from your speakers. Alright, so this is how the particular amplification thing happens inside the microphones. Alright, so transistor is the device which actually works as the amplifier. You can say like this is the main part of the amplifier, the transistor. Alright, so let me just give you a faint idea or a vague idea about amplifiers. Suppose you have this AC signal. Alright, so along the y-axis I have written your input, right? So I can write down V input, okay, and please make it a proper diagram because this is really sketchy. Okay, so I am inserting this particular AC signal since it has got plus minus alternating cycles. Alright, what I am doing is I am inserting into an amplifier, which is like this kind of a device which has two terminals. Amplifier, it has two terminals. Alright, two terminals, please remember that it has got two terminals. So X and Y, these are basically your, suppose X, Y are your input terminals and X dash, Y dash are your output terminals. Alright, these are your output terminals. Okay, now what happens? How will you get the this thing? Amplified signal you are going to get. This will be your graph for your output. So V output versus T graph. So you can see that there is an obvious amplification of the signal that had been fed into the amplifier. Now please note that the amplifier is actually connected to an external source. Okay, it is external energy source. Otherwise, what will provide the required amount of energy to amplify these signals? It requires some amount of energy to amplify the signals. That means to increase its amplitude. Alright, so the increase in the amplitude of the signals is because of the energy which is being externally supplied to the amplifier. Okay, so transistor connections as an amplifier when we'll be studying, okay, whenever we'll be studying the, you can say, connections of the transistor as an amplifier, there are three possible ways in which you can connect a transistor so that it works as an amplifier. Okay, now this particular three different ways is arising because a transistor has three terminals, but an amplifier has only two terminals. So you need to have a common terminal which can be common between your input and the output circuits. Okay, so that you can reduce your total number of input terminals into 2 as well as your output terminals into 2. Okay, so that is about it. Just a second, let me write down or list down the three different configurations in which you can use the transistor as an amplifier. Alright, so transistor is a three terminal device. What is the need of the configurations? Study three terminal device transistor, and amplifier is a two terminal device. That is why you need to have the different configurations. You need to have a common region. So according to that, you have a common base amplifier, you have a common emitter amplifier, and you have a common collector amplifier. Alright. In common base amplifier, please note this is your NEET hotspot. Direct questions will be asked based on the data that I am providing you right now. In common base amplifier, your input is the BE junction and the output is your BC junction, right? So basically you can see that the base is the common. That is why common base amplifier. Similarly, you can write down for the input out here, you have base emitter and emitter collector as your output. And for common collector amplifier, you have emitter collector as your input. Base collector as your input and your emitter collector as your output. Alright, so in this particular thing, you can see that the collector is the common one. That is why common collector. Alright, now for your NEET, this part is the most important, and in your books also you will be mostly dealing with the common emitter amplifier. So we will be studying the working of the common emitter amplifier. Okay, without further ado, let's just start up with the construction and the working. Okay, before I start up with the working of the CE or the common emitter amplifier, configuration being used as a transistor amplifier, let me just tell you a little bit more about the transistor phenomena, like how is the transistor actually being used for amplification. Alright, let me just give you a brief insight into it. Actually, what happens, the base emitter junction, as you can see, the base emitter junction is always what? Forward biased. Yes or no? Now, whenever you have forward biasing, the resistance is low. That is why the milliampere current can flow in the forward biasing region, right? So resistance is low. Alright, resistance is low. But when you talk about the emitter, you can say the output circuit, that means base collector junction, that is base collector junction. Okay, base collector junction, that is. At that time what happens? You have reverse biasing. Right? You have reverse biasing. So in that case, your resistance is high. In reverse biasing, microampere current flows and resistance is very high. Right? So let's call this resistance as RBE. Let's call this resistance as RBC. Alright. In this case, obviously base is the common one. So you can consider that we are talking about the common base amplifier in this case. Alright. Although this concept is applicable and extensible to the common emitter amplifier as well. But this I'm just trying to explain you how the emitter works, how the amplifier works. Alright, why is the amplitude of the output being magnified, or you can say enlarged. Okay. So basically what happens, the forward biasing, the resistance is low. In the reverse biasing, resistance is high. If you know the power formula, then you can write down power dissipated for the base emitter junction, which is forward biased, is IE square REB. IE is your emitter current. Alright, IE square REB. And let's talk about the why we are taking IB, why we are taking IE, why we are not taking IB. The reason is that we have to consider a current. We have to consider currents whose magnitudes are almost comparable, so that we can compare the power dissipation of the input and the output circuits. Okay, so you already know that the input circuit is a lower power. Obviously it will have a lower power dissipation as compared to the output circuit. Output circuit has a greater power dissipation. Alright, so basically P base collector that you have, that will be IC square into R, you can say BC, right? Now IE and IC are comparable numerically. Yes or no? So you can easily know, you can easily write down that since RBC is obviously far greater than REB because of reverse biasing and forward biasing respectively. Therefore, you can write down PBC is far greater than PEB. Right? That means the power that is dissipated in the base collector junction or the base collector circuit is much higher as compared to the power which is dissipated at the emitter base circuit, right? That means the output power is far greater than the input power. All right. So this is the amplifying action of the transistor. I hope you have understood this. But why is this transistor so called? Like transistor. This transistor is actually a combination of two words, transfer and resistor. Alright. Okay. So basically what is happening, if I don't know if you have noticed or not, the current is being transferred from a circuit of low resistance to a circuit of higher resistance. Normally we know that current will always choose the path of least resistance, right? But in this case the current is being transferred from the circuit of lower resistance to the circuit of higher resistance. That is why it is known as a transistor. All right. Okay. So and in doing this, in transferring the current from the circuit of lower resistance to the circuit of higher resistance, the base plays a very important role. Particularly the base being lightly doped. Okay, this particular phenomena is actually the governing you can say or you can say it is the main reason why you can transfer the current from a low resistance circuit to a high resistance circuit. All right. So in particular this transistor, you will have a term called transductance. Okay, transductance. So transductance is basically transfer conductance. All right, and it has the same unit as your Siemens or mho, you can say. Okay, so transductance formula you have to keep in mind. Questions will come directly from here. In your syllabus, not much has been commented upon the transductance formula, but in NEET I have seen questions coming, so please note it down. Okay, it is the ratio of the change in the collector current to the small change in the emitter base voltage. All right, so you can note that down. Ratio of the small change in the collector current to the small change in the emitter base voltage. Okay, and this GM or the transductance, you can write it down. It depends on the geometry, doping levels and biasing of the transistor. Geometry of the transistor, the doping levels, okay, and the biasing of the transistor. Alright, if you are thorough with this particular thing, let's now move on to the working of the common emitter transistor. We will take common base also. For now, let's just content ourselves with the construction of common emitter transistor. Please have a look out here. Obviously, I am going to start up with the transistor symbol, right? Okay, so I am doing the PNP out here, okay? PNP. And of course, this is the base, this is the collector, this is the emitter. From P to N, the current flows, so my direction of current flow is this. Alright, so I am writing out here. Please have a closer look. This is going to be your input and this is going to be your output circuit. Right, this is going to be your input and that is going to be your output circuit. And we are taking what? We are studying the NPN or PNP. We are taking PNP. Alright, NPN can also be drawn accordingly only. I'll draw it after I have explained the PNP transistor as the common emitter amplifier. You can give the heading also. Working of a common emitter PNP transistor as a common emitter amplifier. You can pause the video and give the heading. Meanwhile, I'm just proceeding with the entire diagram. Okay, working. So you can see you have a PNP transistor from emitter to base the current is flowing, since from P to N always the arrowhead is going to be directed. Alright. So the base current will be flowing in this direction and the emitter current will be flowing in this direction. So you know that the base current is negligible. Yes or no? It is negligible. And you also know that we have to do the input circuit has to be forward biased. So we have to do the forward biasing of the input circuit, right? So I'll just write it out here. See, I'll just write it out here. Since this is N, so I'm connecting it to the negative terminal, right? I'm doing it this way. Okay. Now this is my, if I connect a voltmeter out here, this is my input voltage. Yes or no? This is my input voltage. This particular part, I will call it the VBE, the potential difference between the base and the emitter junction. Please note that the battery that you can see out here, which has been used for the forward biasing, will be called as the VBB. Alright? Okay, now VBB and VEE, they are different. They are not the same. Okay, they are not the same. VBE is the difference between the potentials of the collector and the emitter, while VBB will include all the other aspects like the resistance of the conducting wire and everything. Okay, so the VBB and VBE are slightly different. Okay. Now, please do one thing. You connect, since you are trying to study what? You are trying to study the function of the transistor as an amplifier. So obviously you need to have what? You need to have an input. You need to have an input of AC. So I am writing it as EI. Alright, what am I writing it as? I am writing it as EI. This is the AC signal which you wish to magnify the amplitude of. Alright, so you can write down AC signal with lower amplitude as an input. Lower amplitude as an input. Okay, so it has been fed into the input circuit which is forward biased. Okay, and this is base biased PNP transistor in the common emitter, and it is common emitter configuration. Alright, why I am saying common emitter? Because see, this emitter, this is the emitter, this I am connecting to the output circuit as well. Alright, so now the output circuit has to be reverse biased. So we have a P out here. We are going to attach a load resistance out here. And we are going to give it reverse biasing. So this is my reverse biasing that I have done, P to N, right? So it is reverse biased. My collector or the output terminal has been reverse biased. This particular potential difference will be called as VCE, or the potential difference between the collector and the emitter terminals. Alright, so out here across this, if you connect XY, then this is your output, V output. Alright, this is the V input, this is the V output. You can actually attach a voltmeter out here also. You can attach a voltmeter out here also and call it V naught. Alright, across the load resistance. So this is your basic construction. This you will call it as VCC, or the output voltage. You can say the VCC. VCC is basically the battery which is helping in the reverse biasing of your collector. Okay. Now the input that you will be taking, the input AC signal is, where is my cursor? Just a second. So the input you will be taking as this. Alright, suppose this is EI and this is T. The output, please note down the output. What will the output be like? The output is going to be reverse. First of all, it is going to be reversed. That means there is a 180-degree phase reversal. Alright, this is a question in NEET. Between the output and the input of your common emitter transistor being used as an amplifier, what is the phase difference? So you need to remember that it is pi. Pi is the phase difference between the input and the output voltages of your amplifier, okay, which is being used in the common emitter configuration in your PNP transistor. Okay, so each and every detail you will have to remember. I hope you can remember this. Okay. And one more formula I'd like you to write, which is basically the application of Kirchhoff's law applied to these two input and the output circuits. You can directly write the result. V naught is equals to VCE equals to VCC minus ICRL. IC is basically your output current, RL is your load resistance across which you are connecting your voltmeter, output voltmeter. Alright, so this formula you please remember. Okay, if you have remembered this, V output, this is V naught, this V naught is what we are talking about. Okay, so input and output, this is your input signal and this is your amplified output signal. Okay, this is the function of this particular transistor being used as a common emitter amplifier. PNP transistor being used as a common emitter amplifier. Okay, so basically what you are doing, you are taking this, you are taking this particular signal, you are taking the AC signal, you are superposing it into a constant voltage which is VBB, and then this is resulting in an output voltage, the output voltage. Therefore, you can actually get a IC in this direction because of the production of IB in this direction. Okay, I hope everything is clear to you. And the phase relationship is very important. Phase relationship is very important. Relationship is very important. So don't make a mistake out here. Okay. Basically, for your positive half cycle, this will give you a negative half cycle. Right? It is going to give you a negative half cycle. Right? That means as the input signal goes through its positive half cycle, the amplified output signal is going through its negative half cycle. That is the 180-degree out of phase or in opposite phases. Right? That is the part from where the question is coming. Okay. Why is this happening? When the AC signal is fed to the input circuit, like in here, when the AC signal is fed to the input circuit, alright, its positive half cycle increases, right? Its positive half cycle increases, right? And that in turn increases the forward bias of the circuit, right? Yes or no? The forward bias will also increase. This increases the emitter current because the IB increases. Okay. As a result, what you can say is that across the collector current that you have out here, this will also be increasing, but it will be increasing in the negative direction. Why will it be increasing in the negative direction? Because there is a potential drop across RL. Alright, there is a potential drop across RL. Okay, this is what happens. So you can write it down in your own words. This part is not much asked, but just for the concept clearance, I just told you. Okay, fine. If you have copied everything that is taught so far, let's talk about the current, voltage and power gains of our common emitter amplifier. Please give the heading current, voltage and power gains of common emitter amplifier. Please give the heading current, voltage and power gains of common emitter amplifier. Please note down these formulae. These are very, very important. Direct questions are asked from here. Beta AC is basically your current amplification factor, and this is, since we are talking about transistor being used as an amplifier, we will talk about AC gains. Because your input is AC. Input is AC. That is why we are talking about AC gains. The amplitude of the AC is increased. That is why we are talking about the gain in the AC current. Alright, therefore AC gains. So, in your DC current gain, you will write it as beta DC. This works when you are using the transistor as a switch, if you remember. Now, since we are talking about the transistor being used as an amplifier where the input is in AC, so we will talk about AC gains. Therefore, the current amplification factor is in AC. So, AC current gain. This is known as AC current gain or beta AC, or you can also call it AI. The definition of AI is small change in the ratio of the small change in the collector current to the small change in the base current, provided your VCE is kept constant. Provided your VCE is kept constant. Alright. If you talk about the DC current gain, please note out here we are talking about the ratio of the small change. What are we talking about? Ratio. Ratio of the small change. We are not just talking about ratio, but the ratio of the small change. That is why this is AC. Alright, that is why this is AC. Now, if you talk about DC current gain, okay, which will be beta DC, this will be ratio of the collector current to the base current when VCE is kept constant. Alright, simple enough. Alright. Let's now talk about the AC. Let's talk about the voltage gain now. AC voltage gain, which is also written as, just a minute, which is also written as your, just a second, let me take it the next screen. AC voltage gain. This we are talking about the voltage gains. Alright. Please give the subheading voltage gains. We have completed talking about the current gains, AC gain and DC gain both for an amplifier. Okay. Now we are talking about the AC voltage gain. We will also talk about the your AC power gain. Okay, we will also talk about the AC power gain. So AC voltage gain, if you talk about, then it is defined as AB, and it is defined as the small change in the VCE divided by small change in the VBE. So VCE is your output circuit voltage, VB is your input circuit voltage. Alright, so obviously you can consider this as the voltage gain. Alright, now what is important to note out here is, just a second. What is important to note out here is that delta VBE can be written as what? It can be written as Ri into delta IB. IB is your input current and Ri is what? Ri is basically the resistance of the input circuit. Okay, you can write it down, resistance of the input circuit. Alright, so delta VCE, right? VCE can be written as minus R naught delta IC. Okay, what is the significance of the negative sign out here? It indicates the phase reversal. It indicates the phase reversal because you know now input, if it is this like, then your output is going to be your this like, right? If this is your input, let it be EI input, then this is your output. Okay, this is your output. So there is a 180-degree phase reversal. That is why there is a minus sign out here. Alright, and RO is the resistance of the output circuit. Resistance of the output circuit. I hope this much is clear to you. Right? Now, let me just take up the next slide. Just a second. Copy all these things down. Meanwhile. Now let's talk about AV only. AV is equals to delta VCE divided by delta VBE. So delta VCE we wrote down what? We wrote down minus R naught IC divided by R internal input and IB. Right? Now please look at it. IC by IB, does this remind you of something? Does IC by IB remind you of something? Delta thing is also incorporated. No? Delta IC by delta IB, does it remind you of something? This is beta AC. So minus beta AC into R naught divided by Ri. This R naught by Ri is sometimes known as the AR, or the you can say AC resistance gain. AC resistance gain. You can write down AC resistance gain. Alright. So basically AV can be written as the product of, just a second. AV can be written as the product of your AI, which is basically your beta AC minus AI. No, sorry, only AI, because AI itself is your, what is AI? AI itself is your beta, right? AI into AR. Okay, the negative sign is not incorporated out here. Okay, don't incorporate the negative sign out here. So the voltage gain is written as current gain into resistance gain. Okay, questions will be coming directly from this particular topic, so please note it down properly. Meanwhile, I am changing the slide. So now we will talk about AC power gain. Right? So AC power gain is basically change in the output power divided by change in input power. Change in output power divided by change in input power. Alright, so it can be written as delta IC whole square R naught divided by delta IB whole square Ri. So you can easily write down beta AC square R naught by Ri, which is AR. So you can easily write down beta AC square AR. Okay. Now obviously your beta AC square is far greater than alpha AC square. What was alpha AC? Do you remember what alpha AC was? If not, then please get back to your alpha value, okay, and give it a revision, quick revision. This will help you out. and definitely you will be able to understand why it is greater. Okay, so this is kind of your homework to figure out why beta AC square is far greater than alpha AC square. Alright, now let me just quickly take the construction of the NPN transistor as a common emitter amplifier, because sometimes the questions will come from there also. So I'm just writing it down. Out here I'm taking the transistor. Just a second. I'm taking the transistor out here. Alright. Now suppose this is the base, this is the emitter, this is the collector. And we are talking about NPN now. NPN. So from P to N the current will be flowing. So this is the direction of the arrowhead. Right? Okay. So actually it will take up a lot of time. Do one thing. This NPN transistor circuit you just try to make yourself. Okay, transistor as a common emitter amplifier. Don't start this way. Take it this way only. Like keep the construction consistent with the previous construction. Like the base was out here, the emitter was out here, the collector was out here. That way it will be easier for you. Okay, try with this. Try to construct the NPN common emitter amplifier. I'm sure you'll be able to do it. Alright, so the base and the emitter junction has to be forward biased, right? And this is basically your input circuit where your EI has to be supplied, or it has to be superimposed up, on top of the VBB, right? And your emitter collector junction is basically your reverse biased, that is your output circuit, and the E output you will be obtaining in the that particular circuit only. Alright, so you can please try it yourself. I'm not taking it because the video is already getting a lot bigger. So now let me talk about the characteristics of common emitter configuration, because the common emitter actually configuration is very much asked. Okay, the characteristics, I'll just quickly take it. Please write down, give the heading, characteristics of common emitter configuration of a transistor. So I'll give you 3 different graphs: the input characteristics, the output characteristics, and the transfer characteristics. So let's start up with the input characteristics. I will draw it in one particular slide only, so it's easier for you to compare. Output characteristics, and third is your transfer characteristics. Transfer characteristics. This I am drawing for, I'm specifying for which configuration also I am drawing. It is for your CE, common emitter configuration of the transistor. Alright, so input characteristics, please write down. In input characteristics, your forward biasing is done. So the current which is flowing is in the milliampere phase. Okay, so milliampere, this is your current along your y-axis, and along your x-axis you have your volts. Alright, in volts only you will have the voltage. Alright, so the current is this like. Okay, so this is base current. This is base current. Please write down. This is base current. Base current. Okay, the variation of the base current IB with base emitter voltage VBE. Okay, and what about the collector emitter voltage then? Collector emitter voltage is kept constant. Alright, so for two graphs you can see out here, no? The first graph is for your lower VCE, say VC equals to 4 volts, and this particular graph is for a higher VCE, say 10 volts. Alright, okay. So you can see out here, you can see in this particular graph that base current versus VBE, VBE is also in volts. This particular graph will give you the input characteristics. Alright, now VBE is what? Your VBE is basically your barrier voltage. Alright, this is what? This is barrier voltage. Okay, so basically your base current will be smaller. Base current will be smaller if your forward biasing is lesser, right? Okay. So basically, as you are increasing your VCE, as you are increasing your VCE, what happens? As you are increasing your VCE, alright, sorry, there was some technical problem with my pen tab, so I got a little bit distracted. Okay, so here what I was saying is, this is your input characteristics, and this is your base current, which is your IB, right? And this is your base emitter voltage, right? So we are noticing the base emitter base current. We are noticing the base current with respect to two different collector voltages, which is VCE and VCE at 4 volts and VCE at 10 volts. Alright, we are noticing it at two different voltages. Alright, so in this particular state, in this particular thing, you can calculate the RI. You can calculate the RI. What is the RI? What is the RI? RI is basically your input resistance. You can calculate the RI. Just a second. You can calculate the RI. How to calculate the RI? In this common emitter configuration, it is defined as the ratio of the small change in the VBE. Please write down VBE, which is the base emitter voltage, divided by delta IB. Alright, at VCE kept constant. So this is the input resistance at VCE kept constant. Alright, so input resistance you can take out by understanding the input characteristics of the CE configuration of a transistor. Alright. So basically the input characteristics, whenever it is non-linear, okay, since it is non-linear, so the RI will also vary at every point. Okay, okay. So at every point, if you want to calculate the input resistance, you will have to take the slope on the curve of base current versus VBE. Okay, now let's talk about the output characteristics. Let's talk about the output characteristics. The output characteristics is basically, let me just draw the graph for you. In this particular case, along your y-axis, you are going to take your collector current or IC. I'm just writing down IC, which is of course in milliampere. Alright, it is in milliampere collector current. And your collector emitted voltage will be in your x-axis. Okay, okay. So you are considering the output current and output voltage. This was your input current and input voltage. So output current and output voltage, if you draw the graph, then obviously you will have to draw the graph for IB kept constant. So IB, when it will be kept constant, you will have these two, you can say, these two shaded regions. Please draw these shaded regions first. These shaded regions, from these shaded regions, questions come. Okay, I'm writing this particular end as A and I'm writing this particular end as O. Alright, now this shaded region which is there below the, how to write this out here? O dash. The shaded region below this O dash, this is basically the region where the transistor can work like a switch which is placed at the off situation or condition. Alright, so in this particular region it will be off, the switch will be off, and in this particular region the switch will be on, because see, IC is maximum in this case. IC is maximum in this case. Out here IC is minimum. IC is minimum. Alright, so this corresponds to the saturation operating region or the saturation region, and this corresponds to the cutoff region. Alright, I hope this part is clear to you. Now the output characteristics, in the middle also you will have many different these kind of curves. Alright, many curves of this kind. This is basically the first graph that you had, below which we had considered the shaded part. Okay, that is basically your when IB equals to 0. When IB equals to 0. So when IB is equals to 0, then IC is also equals to 0. That is why it is present in the cutoff region, right? So as a result, you can say the switch is turned off. So in these shaded regions, OA, the shaded region below OA and the shaded region below OB, these are the places or these are the regions where the transistor can be used as a switch. And in the middle part, I've made a little bit a mistake in the drawing of this diagram. Please make it this way. Okay, I mean this line should be touching these particular lines. All right. This will be your operating region operating region or active region, or active region. In this active region, we can use the transistor as an amplifier. Alright, so out here this IB, let it be 10 microampere. This IB is basically, let it be 20 microampere. Then so forth and so on, you will keep on increasing the IB values. Alright, as a result, see the saturation current is also slowly increasing. Okay. So by a value of 10, you can just keep on increasing, and this will also keep on increasing. Okay. Next, let's talk about the transfer characteristics. So before that, we have to take the output resistance. So it's simple only, no? The output resistance will be equal to delta VCE divided by delta IC, where IB will be kept constant. Okay, this is all about the output resistance. Alright, but of course you have to keep the base current constant. Right. So transfer characteristics, let's talk about the transfer characteristics now. The transfer characteristics is a fairly simple graph. It is a linear graph. Alright, it is a linear graph. And the thing is, along your y-axis you have to take the transfer characteristics. Along your y-axis you will have to take the milliampere collector current, and along the x-axis you will have to take IB in microampere. So please correct this one. Out here it won't be milliampere. This is going to be microampere. Since this is base current out here, I just made a mistake out here. This will be microampere base current. Alright. Although this is forward bias, but the base current will always be in the microampere because of the low doping of the base. Right? Base is thin and it is lightly doped. That is why very small amount of recombination will take place, which will result in a very small amount of base current. It will be in the magnitude of the microampere only. Okay, so you can see out here we have drawn the graph of the transfer characteristics. Alright. So along your this x-axis you have the IB, which is basically your microampere in microampere, and IC is in milliampere. Okay, so you can just for an idea, you can make these demarcations in the graph. Suppose the IC is 5, this is 10. 5 milliampere, 10 milliampere. So correspondingly out here it will be 100, it will be 200 this way. Alright, 200 microamperes. This way the change will be taking place. Suppose the VC, that is the collector voltage or the output voltage, is kept at 4.5 voltage. Okay, volts basically. Okay, so this is all about your the different characteristics. If this much is clear, now we will be talking about transistor as a common emitter. Sorry, that is already done. Let's talk about common base configuration. Also you can draw. Same kind of principles will be used. Input circuit has to be forward biased, the output circuit has to be reverse biased, so on and so forth. The AC signal has to be connected to the input circuit, and the output will be received in the output circuit, obviously. Alright, so next let me talk about transistor as an oscillator. Alright, I'll be taking this in the next video, because this video has already become very long. Okay, so maybe there'll be some problem in uploading, so I'll just take it in the next video. Thank you so much. Keep studying.